Looks like we're getting settled here. I think we're ready to begin. Hello, everyone, and welcome to the AGU hosted webinar on the Fagradalsfjall eruption in Iceland. I am Dr. Owen Anfinson from Sonoma State University, and I will be your moderator along with Dr. Morgan Jones from the University of Oslo. I'll leave a more proper introduction and welcome to our first distinguished speaker, Dr. Freystein Sigmundsson. But I wanted to let you know the framework of the webinar and how to ask questions. The 6 speakers will give a 10-minute talk for the first hour, and then all questions will be answered at the end of the webinar during the 30-minute Q&A. In the chat, I have put some information on how to direct your questions to the speakers. Essentially, use the @ symbol, the speaker's first name, and then type your question. Morgan and I will curate the questions and we'll try to get as many of them answered as possible. Lastly, I'd like to thank Heather Naley and Victoria Forlini of AGU for hosting the webinar, and our NORAM Arctic team led by Dr. Carmen Guiena from the University of Oslo for assembling the speakers and putting this all together. And with that, Freystein, the floor is yours.
Thank you. Sorry, let me. Owen, can you confirm you can hear me?
I can, you're good.
Yes. So welcome everyone. My name is Freystein. I want to give you a little bit of introduction and welcome. I have some co-authors that have contributed slides to what I will show, and a second group of people that I've been collaborating with to understand better the precursors to the eruption. So first of all, where is this? We have a series of talks that will, following my talk, will discuss the overall tectonics and plume dynamics in the North Atlantic. But a little bit on the exact location of the eruption. It is here in Iceland, Reykjavik, the capital of Iceland is here, international airport here, and it is a basaltic lava eruption, and it is occurring above a dike intrusion. A little bit about the tectonic setting. This is happening in an oblique spreading zone where the spreading rate is about 2 centimeters per year. But it is really important when we are trying to understand the activity here to understand the fact that there's a lot of shearing going on across this plate boundary, and it has resulted in these fissure swarms that you see. And Fagradalsfjall is a separate, we can call it volcanic system, but it does not have a very extensive fissure swarm. And importantly also, there are these north-south oriented faults in black here. So this is not a typical transform fault. It is more like a zone of bookshelf faulting, but this is all interacting at this site. And importantly, it's a part of an unrest episode that has been going on since the beginning of 2020, involving several volcanic systems and stress triggering between them. And here is a recent paper that has been published by or led by the team at the Icelandic Met Office, and Svartsengi is one of the neighboring system that is involved. But in this eruption, what happened? Well, there was importantly a period of tectonic deformation and earthquakes before the eruption. So the vents of the eruptions are in this area here, and this is Mount Fagradalsfjall. Dike intrusion as inferred from geodetic models here, and many of the north-south faults and this sort of broad area that is the central axis of the plate boundary in southwest Iceland had some activity and faulting. And importantly, there was a very active period of 3 weeks of intense seismicity prior to the area. So the dike event was ongoing in this area, but there was a lot of tectonically triggered earthquakes in this area. Black stars here with earthquakes, magnitude 4 to magnitude 5.7, 30,000 earthquakes. Many felt, about 29 earthquakes felt, and many of them here in the capital region of Iceland. So this was something everyone in Iceland was very well aware of. And we saw some surprises. For example, decreasing earthquake activity prior to the onset of the eruption. So there was a dike eruption, and we could see this also in the ground deformation very well. This is an sentinel interferogram showing ground displacement shown as fringes, where each fringe corresponds to 28 millimeters. This is from 23rd of February to 1st of March, but if you look at GPS time series, we could see steady evolution of displacements. In total, the deformation is over 0.5 meter on the surface. And one thing we are studying and is somewhat strange is that the deformation rates, they decayed and reduced before the eruption. So everything started very abruptly. Now, in terms of the eruption, and in addition to the talks that will be presented here, there are many other teams in Iceland and internationally working on the eruption. Includes Ármann Höskuldsson, Þorvaldur Þórðarson, and Ingibjörg Jónsdóttir at University of Iceland that are studying the many phases of the eruption and derivative products, and there have been periods of widely different activity, steady effusive lava flow activity, rhythmic fountaining, and of course a lot of social media attention to this eruption that has been very accessible. A little bit of tephra produced, and as well as with the lava types that have been produced, the tephra is of different types depending on the activity in the crater, whether it is due to boiling, fountaining, or fused, and I anticipate that there will be numerous studies of many aspects of the eruption in addition to those presented here. Just to end, maybe what has been happening at this eruption since 2nd of May until today was very regular behavior, where the eruption tremor picked up every about 10-minute interval. This is a 1-hour spectrogram. It shows 6 lava events where magma was flowing out of the crater. That is the time when we see tremor, and this was the situation really until today, where it seems to have changed, where this type of very regular activity has changed and is becoming more regular or steady outflow from the crater. And I think there's a lot of potential for more research where we combine well the different observations types we have of these eruptions. And with that, I think I stop. But as I say, the program ahead, we go to the very wide questions, why volcanic activity is happening in Iceland, and then we focus in this webinar on specific aspects. And important has also been the response of the civil protection that has allowed good access of public and media to this eruption, so it has become very popular on the media. Thank you.
Thank you, Freystein. It is amazing how they've been able to give everybody access to it. It's actually quite wonderful. So now let's take a look at the larger tectonic setting with Dr. Grace Shepard from the University of Oslo. Grace?
Yes, hello everyone, and thanks again to the organizers and to AGU for this very exciting webinar. So yes, my name is Grace, and I was asked to talk about Iceland in its sort of zoomed out, bigger picture setting. So I'll talk about some of the tectonics and the geodynamics of this region. And when I introduce this sort of scale change, just to remind you that it's part of the global system, whether we're looking at Iceland, a plate, or the world itself. And there's sort of 2 ways that we can start to approach this topic. First is through considering it through a vast spatial scale. So whether we're looking at an individual eruption or even smaller scales than this, through to the regional setting, up to its global setting. And of course, this is just the surface. There's a lot of things happening beneath our feet. So we can peel back the Earth. Here's just a snapshot of what it looks like at 200 kilometers depth. And indeed take a slice sort of through the Earth from the surface down to the core. So spatial aspects are one thing, and the second element is time, specifically deep time. So the rest of the speakers, I think, will talk a lot about present day and sort of daily timescale processes and even into the future. But what I wanted to do, at least for these 9 minutes, is to take us on a journey back. So we can look at present day, of course. We can say, let's go back to 50 million years ago, to 100 million years ago, 200. So here's just an animation going back in time showing the motion of the tectonic plates. And just so we're on the same page, MA means millions of years ago. So yeah, already you can start to see that I'll talk a bit about Iceland, but also Iceland in its bigger global setting. And Iceland is unique for many, many reasons. But from this perspective, it's got two really great things happening. First of all, it's located on a plate boundary. And second of all, it's got a mantle plume underneath it. So when we're talking about the plate boundary, what we're referring to is the divergence between the North American plate and the Eurasian plate. And so the plate boundary is generally designated as this region here. And in the Atlantic, what we've got is a mid-ocean ridge, which is spreading apart and creating seafloor along this boundary. Secondly, we've got a mantle plume. So this is a hot thermal, likely thermochemical anomaly rising from the Earth's interior. And so Iceland is unique because it's got these two processes happening in the same place. So here we can see the plate boundary on the surface and the mantle plume in the mantle deep below it. And if we continue this journey of rewinding to a time before even Iceland existed, but I hope this will give some context as to why it exists, the processes happening, and what even might happen in the future. So first we'll focus on the opening of the North Atlantic, so the plate tectonic side of the story. So you can see Iceland in this figure and the plate boundary, which runs from the Arctic down towards the central Atlantic here in yellow. To the north and the south of Iceland, we have the Kolbane Sea and the Reykjanes mid-ocean ridges respectively. And it's worth just noting that there's also an extinct ridge, which means that there's no active seafloor spreading happening today, but it did in the past. That's the Argyll Ridge. So this is present day, but we actually know that the ocean floor within the Atlantic was created around about 56 million years ago. And we can look at lots of different geological and geophysical data sets, but one of the primary ones that we look at is magnetics and magnetic anomalies. So this is what's shown in the background here. And what we can do is make these what's called magnetic picks related to these magnetic anomalies and assign them to a time. When we have enough of them, what we can do is draw lines, which are called isochrons, and they link up seafloor at the same age. And so this is a map of the age of the seafloor for the North Atlantic. And you'll see in the center of the Atlantic, it's very young, new ocean seafloor, and towards the continental margins, it's a lot older. It's got these darker colors. So I'll just simplify that figure. Everything that's an oceanic rock is in gray with the isochrons on the top, plate boundaries in black, and you can see the topography at present day just for reference. And the remaining yellowish colors are the continental, submerged continental rocks that are today submerged. So we'll go forward in time. Again, this is at present day. Take a step back to 10, 20, 30, 40, 50, and 60 million years ago. And you can see at this point, Greenland was snug up next to the Norwegian margin, and none of the North Atlantic actually existed. And I'll just show this animation, which will run backwards in time and then forwards in time. So we'll see this opening and closure, apparent closure of this ocean. But I just wanted to say that the story continues before 60 million years ago, and it was actually a period of long-lived, over hundreds of millions of years, rifting between Greenland and the Norwegian margin. So as Freystein said, the rate of motion that's occurring across this boundary is about 2 centimeters per year. So that's about what our fingernails grow at. And for the North Atlantic, this is in the regime of what's called ultra slow to slow. So there are other ocean basins that are moving a lot faster than the North Atlantic. So it's been roughly 2 centimeters per year throughout its history, but there have been some deviations on million years sort of timescales, which you can see along the bottom. If we zoom a little bit back into Iceland, in the figure on the right, we can see the Kolbeinsey Ridge coming in from the north, the Reykjanes Ridge in from the south, and then we have different zones of rifting. So there's been an overall shift with time from the west towards the east. So for example, there was a jump in the rift zone from here to here at about 15, from here to here at 7, and from here to here at 2 million years ago. But it's quite a diffuse boundary, and there's volcanism and deformation and extension happening in various places, of course, with the recent eruptions back down here. And this is just a sort of a vertical slice through that area that I was showing, where you can see the lithosphere, so the outer shell of the Earth. We've got the domain of the Western Rift Zone, the Eastern Rift Zone, and this potential mantle plume. So you can see I'm starting to add this plume story back into it. So about this plume. So when it arrived, it's thought to have been around 62 million years ago. And this is occurred at many places across the Earth. And this is often, the eruptive products are called large igneous provinces. So the one in the Atlantic, or the North Atlantic, is called the North Atlantic Igneous Province. And this has covered a wide range of locations, east and west Greenland, around Iceland, and even towards the Scotland margin. And so this is the area here shown in the darker orange. When it erupted, it was 60 million years ago. So if I shuffle the plates back again, this is the eruptive sort of dispersal area. And the plume has been hypothesized to have a diameter, a head, with this arriving plume head was about 2,500 kilometers. So quite a big scale feature. And this has had a number of impacts, including regional uplift and changes, for example, in sedimentary depositional patterns. Brief comment on the mantle plume. Iceland, it's typically thought to have been sourced from the deepest mantle, so at the core mantle boundary. So this is a slice through seismic tomography, and the next speaker will talk about this. But it's basically a method using earthquake data to look at different domains of the mantle. And we have this red area and these bluer areas. And these red areas on the core are thought to be the source of many mantle plumes. And you can see Iceland is this one located up here, and it's on the edge of this big, slow domain that exists under the African area. This is a vertical slice that we've seen just before through the Iceland plume. So this is one particular model out of Oxford, and you can see the plume conduit snaking its way back down to the core. This plume is also inferred from gravity data sets, but the seismic tomography is one of the best ways we have of imaging this plume and can be used complementary with, for example, geochemistry. Just wanted to say that Iceland is, again, taking first place in some things as well, and this is in the plume flux. So this is plume flux against helium-3, helium-4 ratios, and basically this is to say it is the highest output of all the mantle plumes. So here's the Afar plume and here's Hawaii. And this isn't just a static value, it does change through time, and this variable supply of the magma plume stem is often referred to as pulses. So as I've been saying, when a ridge and a plume meet can lead to some pretty interesting things. And we will talk about Iceland, but I just wanted to remind you that the domain also continues offshore. And it's this elevated oceanic plateau, often referred to as the Greenland-Iceland Faro Ridge, because it sort of connects these domains. And this exists because the magmatic output, partially thank you to the plume, the output exceeds the spreading rate. So without the plume, this part of the North Atlantic would probably look very similar to what we see to the south and to the north. But nonetheless, it exists, and there's about 2 kilometers of dynamic support that the plume is thought to give. And as you can imagine, it has a number of important implications, not least leading to Iceland being above sea level, but also to paleo climate and paleo oceanography patterns. And on that note, I wanted to show some work from a colleague who recently published paleobathymetry and paleotopography analysis of the area. So as sea level changes and as the plume and really area goes under uplift and subsidence, this affects things. So this is at present day, or near to 10, 20, 30, 40, and 50 million years ago. So I'll just go forward in time for you. Oops. 30, 20, 10, and 0. Okay, so I think my 10 minutes is up, but this is just to say it is a very complex and unique setting. You've got tectonic plates and mantle convection, and very simply just the North Atlantic mid-ocean ridge and the Iceland plume are the two main contenders contributing to that. And it has a very dynamic history at present day, of course, sort of back to 15 million years ago if we're looking at onshore Iceland, or even 60 and even older for the whole domain. So thank you very much for your attention.
Wonderful. Thank you so much, Grace. It's really cool to see you rewind the clock like that. Now we will have Dr. Nicholas Selly from the University of Dublin help us get a little more detailed view of what is underneath the volcano.
So hello, everyone. Can you hear me?
We can.
Perfect. Okay, so thanks, Grace, first of all, for nicely allowing me to slide into the present day structure of the Iceland plume. And the way we're going to look at it is by looking at actual images of the mantle beneath Iceland, provided by seismic tomography. So as Grace already mentioned, Iceland is kind of special for a number of reasons, from the fact that starting from the fact that it is the only surface planet of the world where the mid-ocean ridge actually is under the air and not underwater. It has anomalous topography, very thick crust, and it's believed to be linked to a very large igneous province that also has been shown before, and here is highlighted in gray. So the way we're going to look at it through this talk is by looking at seismic tomography. So in particular, the speed of seismic waves is related to and is sensitive to the variations in temperature and composition of the medium that it crosses. In that sense, so low seismic velocities mean that they have crossed a medium that is, for instance, hotter than the average material, and high seismic velocity, conversely, a medium that is colder than the average material. So if we take a simpler example in Iceland to start with, like for instance, Hawaii, where we have a very long hotspot chain, which are believed to be formed by a thin vertical plume, and we actually have a look and measure the variations in seismic velocity across the area, we can see actually the structure of these low and high velocity variations within the mantle, as you can see by the excellent work of French and Romanovich in 2015, where in this case you can see a very thin and strongly negative velocity anomaly, highlighted yellow in this case, exactly beneath Hawaii, which of course are an indication for the presence of plume in there. However, if you compare this to Iceland, you can quickly see that by comparing the simple volcanism coming from one point moving hotspot model with the complexity of the volcanism in the whole Northeast Atlantic region, the situation is slightly different. And this prompted a number of questions about what is actually the shape of the plume in Iceland, and how does it look now at present day, considering all this more complex environment with continents and mid-ocean regions just nearby. So indeed, there have been a number of tomographic studies, of course, throughout the past 30 years that tried to solve this mystery. The first one was developed by Wolf in 1997 and notably made it with this image to the cover of Nature, showing a very narrow and low velocity anomaly right beneath Iceland. However, if we fast forward a couple of years, Bymer et al. In 1999 already started to show a somewhat more complex image of the plume, as you can see here, with a cross section, with a mantle plume that not only is slightly tilted, but it's also notably reaching the bottom of the mantle. And not even a year after, Falger proposed actually the contrary theory. By using different methods, she actually proposed that the mantle plume is actually not a deep mantle plume, but it's only within the upper mantle. That has very strong implications about what's the extent of mantle convection and the mixing between the upper and the lower mantle. And if we go further with the evolution of tomographic techniques and the availability of more and more seismic data, tomographic models got more and more complex, showing mantle plumes that is mostly deep, but also heavily tilted. And many of these models are indeed actually contrasting on its final shape. So if we have a look, for instance, at most of these models, so in this case, I'm showing you on the left a map in which we stack the low velocities from 13 different P-wave models in the area. And you can see that most of the body wave models do actually agree on showing low velocity directly beneath Iceland in the upper mantle. However, if you instead look at waveform tomography models that are based mostly on surface waves, you can see that by looking at 330 and 475 kilometers depth, none of these models actually shows a very clear vertical mantle plume being directly beneath Iceland. So this brought up a controversy about the nature and the extent of the Iceland plume that has been lasting for decades. And it is mostly related to two different methods of looking at it. So studies using body waves have dense clusters of vertical rays only beneath Iceland because body waves are diving waves. And so these are often criticized for the fact that in the case of Iceland, where you have dense sampling only beneath the island and nothing on the oceans around it, this can lead to vertical smearing. On the other hand, surface wave studies, like the waveform tomographies that I shown a second ago, are actually, as the name may suggest, relying on waves that sample only the uppermost part of the mantle and typically can reach up to the transition zone and not beneath it. So this together brought up to a controversy that, again, has been lasting for decades and shown and has been motivated by the large variety of different tomographic models that have been published in the area. So indeed, if you look at the distribution of seismic stations in the Northeast Atlantic region, you can tell that this is far from ideal for studying the area seismically, because apart from a very dense clusters of stations in Iceland, here shown in green, a lot of stations in Europe, in North America, and some stations in Greenland, we have absolutely no measurements coming from the oceans around it, and very little measurements from some other relevant areas. It could be, for instance, Svalbard and northern Greenland. So particularly what I'm going to show you now, it's some images that I have produced in a work which has been just accepted for publication by using waveform tomography, but trying to tackle the problem of data coverage by using big data. So in this case, you can see, for instance, a map of the coverage. So again, stations and events in Iceland. And specifically, we're going to use a data set over 6,000 stations, 27,000 events to produce, to constrain our model with 1.2 million waveforms that are to actually produce images of the structure in the mantle beneath the area. So I'm going to show you now horizontal slices at different depths in kilometers beneath Iceland. Starting at shallow depth, you can see that we see low velocities, so again, indicative of hot temperatures, right beneath the mid-ocean ridge, as we would expect it. If we go at greater depth, we continue to see a similar pattern in the ocean, but we also start to see the very high velocities of the thick and stable cratons that form the basis of the North American, Greenland, and European continent. If we go further depth, we can see a more interesting actually shape starting to take place beneath Iceland, but not exactly beneath it. And if we go even further in the mantle transition zone at 485 kilometers, we start to see how these lowest velocities tend to focus actually away from Iceland. So if we actually track down the areas of lowermost velocities throughout the model, we can see that these are not vertical, but they tend to move with depth. And if we use 3D rendering to kind of combine them together, we can actually see that what we're looking at is not a vertical conduit, but it's a very complex, very large scale and tilted conduit that is actually rooted beneath Greenland in the transition zone, but rises at an angle towards Iceland. And if we look at cross-section, similarly to what we have seen before, we can actually see that these low velocities, so if we want the plume stem in the transition zone, rise from beneath Greenland and then are probably deflected southeastwards towards Iceland by the thick Greenland lithosphere. And finally, the reason why they actually stop around the axis of the mid-ocean ridge is because that offers them the thinnest point of the lithosphere, so where the plume flux can try to pond and eventually break out in Iceland and surface in the eruptions that we all have seen the images of. So our model tries to show a story that is slightly different from the vertical plume paradigm that has been discussed before. But so what's the chance that this is actually made up? So we compared it with a lot of independent derived data. And indeed, if we look at past body wave models, such as the one shown in the left, we can see that actually most of these do see low velocities beneath Greenland where we do observe them, but they were previously interpreting them as just a branch of the main plume. In addition to this, we compared our low velocities averaged in the transition zone, highlighted here in the map in the background, with receiver function measurements of the thickness of the transition zone taken completely independently. They're shown here as the circles. And if you look at the values, you can see that beneath Central Eastern Greenland, we have a coincidence, the coincidence of the area of this lowest transition zone on average, and where also it is thinnest. It also implies a hotter transition zone compared to its average values. So finally, to make sure that most of these things cannot be attributed to modeling errors, we simulated a case in which we would have a semi-vertical plume beneath Iceland, shown in the left, and we try to invert it, and the results are shown in the panel on the right. And what this shows us is that if a large low-velocity body would be present at the Iceland, we would be able to image it. And so what we are seeing is actually not due to data or modeling errors. So to conclude very quickly, we have seen that the Iceland plume is a large and deep continuous body that rises at an angle from a transition zone with a degree of complicacy and that is actually superior to what was previously asserted by other tomographic models. But what's also interesting is that beneath Iceland, it is also confined to the upper mantle due to its tilt. So while we do not have the final word in this, what we are trying to say is that maybe this is a possible solution to the very long plume controversy, in that, yes, the Iceland plume is a deep mantle plume, but beneath Iceland, it is actually restricted only to upper mantle due to its geometry. Thank you for your attention.
Excellent. Thank you, Nicholas. It's amazing what we can see at depth now. Now, Dr. Aniko Bali from the University of Iceland will help paint a picture of what this eruption is made of.
Let's take a look at how the rocks of this 53 million cubic meters material look like. Especially if my slides will. Electron images of quenched lava and tephra samples in the first row. And you can see that they all contain macrophenocrysts of olivine, clinopyroxene, and plagioclase, which commonly form glomerophilic integrals. And olivines and clinopyroxenes also contain chromium spinazase inclusions. In the matrix, we can observe in both the lava and the tephra microphenocrysts of olivine, clinopyroxene, and plagioclase. And their composition is very similar to the composition of the rims of the macrophenocrysts. In the quenched lava, we can see very fine-grained mineral assemblages, which are most probably formed on the surface within the lava flow. In the bottom line, you can see that all macrocryst phases, olivine, clinopyroxene, plagioclase, and even chrome spinel, contains glassy silicate matte inclusions, both in the cores and in the rims of the macrocryst. The next slide shows the composition of these melts. The yellow symbols are the composition of ground mass glass. The blue symbols are the composition of melt inclusions collected for post-entrapment crystallizations, whereas the red symbols are the whole rock compositions. And here we plotted the titanium oxide and sodium oxide content as a function of MgO. So you can see there is a broad negative correlation, and many of our primitive melt inclusions have MgO content up to 12%. For comparison, I also plotted the composition of depleted and enriched end member estimated for the Western volcanic zone by Shortland and McLennan. And we have these two end members present because below Iceland, the mantle is very heterogeneous, so they might produce very different compositions. As you can see, the melt inclusions are dominated by the depleted end member, but we have some more enriched compositions also here. If we take a look at the crystals, we can see that the most primitive phenocrysts are actually very primitive. The olivines have forsterite up to 89.1%. Plagioclases have anorthite content up to 90%, and the most primitive glycopyroxenes have also Mg numbers up to 89%. So if I plot the composition of the melt inclusions, hoar rocks, and tephra glass in this diagram, we can see that the most primitive plagioclase and olivine compositions might be in equilibrium with our most primitive silicate melt inclusions. Whole rock-like melt compositions are in equilibrium with olivines and plagioclases with intermediate compositions. And the tephra glass is generally in equilibrium with brims, which are relatively evolved, but we have compositions which are more evolved than being equilibrium with the tephra glass, and these compositions are most probably crystallizing in the lava flow on the surface. This graph shows how the composition of the melt changed as the eruption progressed. And in the first diagram, you can see the change in MgO content, and this is whole rock compositions. The eruption started with a fairly primitive magma composition with MgO content around 9%, but this MgO content progressively increased until the middle of April, and then it leveled off and hasn't changed too much since then. In this diagram, you can see the potassium-titanium oxide ratio, and as you can see, we started the eruption with magma which had very low potassium-titanium ratio, which together with the MgO content increased significantly until the middle of April, and then since then we don't see significant changes. This variation can also be observed in the lanthanum-ytterbium ratio of whole rock samples, and also the lead isotopes starting with a relatively depleted composition towards more enriched compositions in April. If we take a look at the comparison of matrix, the comparison of melt inclusions for rock, we can see in this diagram of MgO versus potassium-titanium ratio that already in the second day of the eruption, where we collected most of our melt inclusions data, we had the depleted and enriched melt present in our melt inclusion cargo. And the whole rock compositions are gradually evolving towards this enriched end member. We can see the same thing in the trace element compositions. In this primitive mantle normalized rare earth element diagram, you can see that as the time progresses, our ground mass classes are getting a more steep rare earth element pattern, but actually much more depleted and much more enriched melt inclusions have been present already in the crystal cargo in the second day. This particular very enriched melt inclusion composition is one of these in this other diagram. Now let's take a look at from what depths these melts are derived from. And in this pressure temperature diagram, which is extremely busy, we tried to condense all our data set. We tried to use 3 different geobarometers: the so-called OPAM barometer, which uses glass compositions, depends on the fact that the composition of the silicate melt in equilibrium with olivine plagioclase and clinopyroxene is pressure dependent. The clinopyroxene melt thermobarometer is based on the pressure-dependent exchange of jadeite component between clinopyroxene and melt. And the gas-based thermobarometers are basing on the fact that the solubility of CO2 is much more pressure dependent than SO2 in silicate mats. So what can we see from this diagram? First of all, the ground mass gases, which are indicated with the yellow symbols, are equilibrated at very shallow depths with the microphenocrysts, and this is consistent with the presence of a shallow dike, which was pinpointed by the geophysicists before the eruption. But you can see that the crystallization pressure of clinopyroxenes are covering a much larger pressure temperature range than what we can see in the ground mass gas compositions. And basically our most primitive clinopyroxenes are crystallizing in submoho depths, and their crystallization is overlapping by the entrapment pressure of silicate mat inclusions and the pressure which is indicated by the Horo compositions. These curves here, 1, 2, 3, etc., are indicating the solubility of CO2 and SO2, or the SO2-CO2 ratio in a basaltic liquid at a given entrapment depth. So if we had a basaltic body, which is degassing between 5 and 10 kilometers depth, it would release a CO2, it would release a volatile CO2-SO2 ratio of 1. If that basaltic body is trapped at 15 kilometers depth, then the CO2-SO2 ratio released from this body would be equal to 2, etc. This yellow field here indicates the results of field measurements, and I think Evgenia will talk much more about this. You can see that the CO2-SO2 ratio released from the vent is extremely high, and it suggests a very deep origin of the magma, basically sub-moho depths. And this is overlapping with our primitive melt inclusion estimates. So the magma can be sourced from as deep as 30 to 20 kilometers. Now let's take a look at this magma composition in a regional context. This is our composition in the MgO versus titanium dioxide diagram. And you can see that these compositions are very primitive compared to the compositions of the historical eruptions in Reykjanes, but also compared to the whole Reykjanes Peninsula in general. And they are in the primitive section of the complete Icelandic basalt database. If we take a look at the isotopic, lead isotopic composition, we can see that these mats are not that ultra depleted, but the eruption started with a relatively depleted mat composition, and then progressively it became more enriched. So basically, at the start of the eruption, we have been sampling a different mantle composition than we are sampling in April and May. And of course, this work is not just mine, but it is the work of the complete geochemistry group at the University of Iceland. Thank you for your attention.
Great talk, Aniko. Thank you very much. Very interesting petrology. Up next, we welcome Dr. Evgenia Ilenskaya to help us understand some of the gases involved and the potential societal impacts of the eruption.
Is the presentation working okay?
Yep, just hit, there you go. You're all good.
Good, excellent. Hi, everyone. Thank you so much for inviting me to give this talk. I am going to be much more above ground than the previous talks.
Evgenia, we can see your next slide, though, I think.
Oh, so you're in a presentation, in the presenter view. Let me just check. There we go. Okay. Is that better?
There we go.
Perfect. Multiple screens. Okay, let me start again. Hi, I'm Evgenia. I'm presenting on behalf of a very large group of brilliant collaborators from Iceland and many other countries. And this image shows the eruption seen from the Iceland Met Office, which is the volcano observatory in Iceland. It's the first time in over 800 years that we have an eruption this close to the capital area of Iceland, where over 60% of the population live. So it's very important for looking at the impacts and what it could mean for if this eruption goes on for a very long time. So the measurements that have been done by this group include many different methods, including infrared with FTIR, ultraviolet with DOAS. We've also taken direct samples of the plume gas and aerosol using filter packs and cascade impactors. And we measured the gas composition using multigas. And we've done this both from the ground, and we've also attached our instruments to a drone in order to be able to get very close to the eruption vent. And we've also been taking samples of the downwind areas, both of the gas and aerosol phase and rainwater. The gas composition in this eruption has been very constant, and the emission rate has been as well, although when we had lava fountaining, it has been pulsating, so on and off with the lava fountains. The carbon dioxide to sulfur dioxide ratio that Eniko referred to has been about 3, which is much higher than for previous basaltic eruptions in Iceland. And this is consistent with the magma being sourced from very deep, approximately 4 to 8 kilobar pressures, or something like 20 kilometers below the ground, below Moho. And this agrees, again, very well with geochemistry measurements that Eniko was showing earlier. This is a triangular plot showing how this eruption compares with previous eruptions in Iceland, as well as Kilauea in Hawaii. It shows the yellow area, which are the measurements we kind of have the greatest confidence in, plots in the relatively water depleted part, as well as being carbon dioxide rich. And the flux has been measured regularly with scanning and traversing DOAS. There is some variability on this plot, but it has been relatively constant in the range of 2 to 4 kilotons per day of sulfur dioxide. This is relatively small flux for eruption on global scale, and much smaller than the most recent eruption we've had before this one in Holuhraun, which averaged over 10 times more sulfur dioxide per day. The change of activity to pulsating on and off lava fountaining has not had a measurable impact on the average daily emissions of sulfur dioxide as measured by DOAS. The eruption is also, in addition to sulfur dioxide, is emitting a lot of trace elements, and some of these trace elements are environmentally important. They are classified as heavy metals by environmental and health protection agencies because they can have impact on the environment and health. The eruption in Fagradalsfjall is emitting as much per day as Holuhraun did, even though Holuhraun was a much, much larger eruption event. This is because the current eruption has much more of these heavy metals in the gas phase proportionally. If we compare it to anthropogenic emissions, this eruption is putting out more than the whole of Iceland put together in terms of anthropogenic emissions, and is much more on par with larger, more industrialized countries such as UK, Italy, and USA. I've plotted up several other volcanoes on this graph just to demonstrate how important volcanoes are as heavy metal global sources around the world. And of course, this eruption hasn't been going on for a very long time. So probably these emissions, although they're high, they have not accumulated to the levels where we should be starting to worry about them. But if this eruption continues on for years or even decades, then it will be very important to understand what happens to these heavy metals, and do they end up somewhere in the bioaccumulation chain. These heavy metals, they are emitted as gases, but as soon as they're emitted, they condense into particulates. And that's something that we have been sampling in the downwind populations as well as the up source. I'm just showing 3 different chemical species on this plot, but the same story applies to almost everything we measured so far. I'm showing sulfate, which forms from condensation of sulfur dioxide gas, and selenium and cadmium, which are heavy metals that you might remember were very abundant in the emissions of this eruption. what we see is that the particulates that this eruption forms, and as well as other eruptions, are extremely, extremely fine. They're smaller than 0.25 micrometers in diameter. That's more than 100 times smaller than the diameter of human hair. And this is important because particles of this size are so small they can be easily inhaled. And the particles, they retain the same size when the plume is drifting into the downwind areas. We see the same fine particles at the source and in our downwind sampling stations. What we also see is that the emissions of these heavy metals from the eruption are high enough to cause a change in the chemical composition of the aerosol in the downwind populated areas. During plume pollution events, the heavy metal concentrations are comparable or higher than some large populous cities around the world that are plotted up there: LA, Chicago, New York City, and London. There is a very impressive effort going on in Iceland in order to forecast and monitor what happens to this pollution and where does it go in order to warn people about it. The Iceland Met Office operates a daily forecasting system of sulfur dioxide pollution using a model called CalPath. It predicts concentration of pollutants at ground level. As you can see on this animation, the wind direction in Iceland is very variable. So within 24-hour periods, you might have conditions where almost every direction from the eruption site is impacted in some way or another. And this is one challenge for the model. Another challenge for the model is to predict how close to the ground the plume is actually being transported, because of course, ground level concentration is what matters for impact on people. And there is ongoing work by the Iceland Met Office and other institutes around the world in order to keep improving the accuracy of the model. In addition to the forecasting, there's also real-time monitoring of air pollutants from the eruption site. And the data measured by many air quality stations is available in real time, and people are encouraged to go and check before they go about their daily activities. And what's been really impressive is that the number of air quality stations has been increased after the eruption started, especially in the communities that are most likely to be exposed, including 2 stations at the eruption site, because as we've heard, the eruption is a huge tourist attraction. People are hiking in, and this was set up to keep them informed about the conditions. We have typically been seeing very high concentrations at the eruption site almost constantly, as shown by the graph on the bottom left. You can see that the sulfur dioxide pollutant is reaching into amber and red concentrations almost without a break. On the other hand, in the downwind populated areas, the pollution is much more periodic. It reaches a peak and then it passes. And as you remember, the wind direction is very variable, so this is what causes that. But nevertheless, the concentrations have reached amber and red hazardous areas. And the animation in the bottom right shows conditions which we also get sometimes, is where wind takes the pollution and it circulates it round and round in a circle over the same area. What this means is that the pollution is trapped and persists in one area for a prolonged period of time, but also changes chemically, so that you might be getting different types of impacts on air quality and health. And this is just yet another challenge that the monitoring and forecasting has to account for. In terms of health impacts, they have not been directly measured for this eruption, but our closest sort of proximal analog is the Holuhraun eruption that happened a few years ago in Iceland. And there have been some studies published on it recently. A study that looked at health impacts in Reykjavik detected increased respiratory problems, including dispensing of asthma medication, people going to see the GP, and people seeking emergency department. And all age groups were seen to be impacted, but children most of all. However, one of the most positive outcomes of this study, I would say, was that successful forecasting and public advisories had a protective impact, it seems. So when the forecasting was done in a way that was accurate and public advisories were issued timely, then people sought the healthcare services less. So the public advisories that were given out then and are being given out now are spend less time outdoors if you are in a vulnerable group. And in Iceland, this would, for example, apply to children napping outdoors during the daytime hours. And this is commonplace practice in Iceland during all weathers and all seasons, is babies and toddlers sleep in the pram. But if parents can be warned in advance successfully, then the impact could be lessened. And I leave you with this picture of a volcanic plume. Thank you very much.
Excellent. Thank you very much, Genia. And just wanted to say thanks to all of our speakers for an incredibly informative update on the pulse of this eruption. We'll now begin the question and answer portion of the webinar, and I'll pass things over to Dr. Morgan Jones. We've been curating some of the questions, but please keep the questions coming, and we'll try to get as many as we can answered. Again, just use the @ symbol and the speaker's name and type it into chat, and we'll try to get your questions answered. Morgan?
Great, thank you very much, everyone. I feel that was a really successful webinar, so thank you to all the speakers. We peaked at 305 attendees, so that's really exciting that we managed to reach such a large audience. We've got quite a few questions that have come in. I think what we will try and do is do one question for each speaker and start with Freystein and then work our way down and then sort of cycle through. But we've got about 2 or 3 questions per person, so yeah, we've got a fair amount to get through. So the first one for Freystein was from Rob at Tokolos. It says, what long-term impacts do you think will emerge as a result of this sudden and international interest? And he's talking about not just the eruption, but earth sciences in general.
I think we have to see. There is a lot of scope for collaboration between different groups. We are learning something new, I think, in many respects, precursors, gas, pulsating activity. The accessibility makes a difference, and there was this huge interest in the eruption because of the media attention. I think we have the opportunity to yeah, if we use it well, to bring together different research groups and different data sets, like seismic tremor and observations of pulsating activity as one example. It depends a little how this plays out, how good the collaboration and the interaction is. What is also special is we have we have opportunities to document the very different types of basaltic eruption activity. All these footage, all these observations available close up. This footage provides the opportunity to document well these different phases of the eruptions and how it evolves. I think there is also, because as time evolves, we have better and better monitoring, and with this, for example, the effusive rates that we have from GROW, and nevertheless there is this different phases of the eruption. I think we can learn about the employment system. So I think we need to see what comes out, and also about the length. If this is going to be a long duration eruption, we have the opportunity to systematically collect observations that can sort of form basis for theories and ideas how eruptions like this evolve. Thanks.
Great, thank you, Freystein. Grace, there's a couple of questions which I guess are kind of related, so I might join them into 2. The first is about whether you think there's a correlation between the arrival of the Iceland plume and the start of the breakup of the Northeast Atlantic. And the second one is there has been some speculation in the past that the Iceland plume may even be related as far back as the Siberian traps. Do you have any thoughts or comments on that?
Yeah, they're both interesting questions, and I guess they're a topic of discussion at the moment. With the correlation between the Iceland hotspot and Atlantic breakup. Yeah, I think there is a correlation, but it is also interesting in the timing. So, I mean, onset of the plume activity, really, they suggest 61 to 62, but then the oldest age of the oceanic lithosphere is about 55, 56. So there's a bit of a delay, and there's also a peak in the North Atlantic products about, I think it's about 53 as well. So the significance of those extra million years, I think, is still open for discussion, but the North Atlantic was undergoing rifting for an extended period of time, basically since the, the Caledonites, the mountain chain, were formed. So it's had, over 200 or 300 million years of rifting. So the final impetus, I guess, or the final force needed to break it up and cause seafloor spreading might have been the plume. And then linking the plume back to earlier times, yeah, that gets into a bigger discussion of plume longevity, if they're deep-seated from a constant thermal source. I guess one of the problems that invoking a purely upper mantle source for these things is what would cause, protracted and prolonged melting for 60 million years. If you're starting to extend it to potential Arctic magmatism at 120, and then Siberian traps at 250, yeah, really getting into discussion of what could be causing that. And then you've also got to keep in mind of what's at the surface today wasn't at the surface in the past. So there's things also moving from the deep perspective and the surface perspective. So I wouldn't rule out any of those correlations, but more work needs to be done. And that's what's really exciting about blending modeling and tomography, and yeah, so.
Great, thank you. Moving on to Nicholas, we have a question from Bernd saying, at Disco Bay in Western Greenland, basalt reached the surface, but is now fully detached from the 3D rendering image that you showed. Why did it get deflected towards Iceland, do you think?
This is a very good question. And actually, if I had a 30 minutes presentation, I probably have shown some more slides that would have answered this partially. And this goes actually and ties in with Grace's work, because when we're looking at Disco Bay, we are talking about basalts that are older. So we have to remember that when we're looking at seismic tomography, we're looking at the present day image. So what has happened since we have been recording, which is only in this case, in my case, since 1990. So we are talking about very much present day, but the basalts in Disco Bay are much older. If I remember correctly, the younger one, it's about 50 million years. So we're talking about completely different timescales. And if you have in mind the plate reconstructions of Grace, and if we assume, which is a big assumption, that the plume was steadily in the same shape-ish as we see it nowadays, and we move the plates on top of it, approximately about the time of the eruption in Disco Bay, the plume was in middle Greenland and possibly right beneath the keel of the Greenland cratons, which are this very thick lithosphere. So if you imagine the keel as a very thick lithosphere and the plume hitting right beneath it, depending on where it is, it would go more in one direction or the other. So of course, as I said, this is a very big assumption, because we see that present day the plume is heavily tilted. So we have no reason to believe that this tilt has been stable across millions of years. So probably this changed. But this is, from the observation that we have at present day, our best guess in this regard.
Great, thank you, Nicholas. Moving on to GROW, we have a question from Ben Ireland. Is there anything to suggest the TADR will continue to increase as it has done, stay the same, or otherwise based on current behavior patterns? And have you done any attempted surveys using UAVs or drones? It would be interesting to know, given all the drone footage coming from the tourists. And thanks, it was a great talk.
Thank you, and thank you for the question. Yeah, so there are multiple groups that are doing drone acquisitions. I have not been dealing with this data, so I'm sure these groups will come out and show some really detailed work that they can resolve with their imagery. I mean, with respect to the evolution of the discharge rate over time, this is very difficult to say. The only thing I can say really is that it has been fairly stable and increasing. It can past experience show that you can have eruptions that decline after this, and it will also tend to increase further and then suddenly stop. So just time, we'll see. Was that all of the questions?
I think so.
Yeah. Thank you.
Eniko, we have a question from Bradley. Why do you think the compositions are progressing to a more enriched compositions with time? Is this a change in mantle source or a change in subvolcanic processes?
It is most probably the change in mantle source. So if you take a look at both the major, the trace element, and the isotopic composition is changing. So what we suggest is that, as said, at the beginning of the eruption, probably a more depleted melt, more coming from the more depleted part of the mantle came to the surface, which was basically overtaken by a melt which is coming from a more enriched and probably deeper source. So beneath the Reykjanes Peninsula and beneath Iceland, the mantle is very heterogeneous, and there are different batches of melts which are being produced, and probably they are mixing around the Moho storage zone in here, and then eventually make it in the surface. But it seems that this temporal change was very interesting for us, because in case of Hurlgrøn, it was just the same material coming up to the surface in 6 months. And this is something completely different, and it is a very striking and very strong change within a month. But it's a different mantle source, most probably.
Great, thank you. Evgenia, Celine asks, do you see more halogens than at Hurlgrøn to explain the higher metal ratios?
No, not really, but it seems that Hurlgrøn is the odd one out rather than Fagradalsfjall being particularly enriched. Hurlgrøn seems to be very low compared to other intraplate and rift volcanoes that we have data for, like Hawaii, Ertale. Yeah, those are the main ones. But yeah, it seems like Hurlgrøn is a strange one rather than yeah, this one being particularly rich. I don't know what that means. What about Hurlgrøn is so weird? Or yeah, so yeah, it's definitely something I want to look into more.
Great, thank you. Back to Freystein. So Rob, that asked the first question, had a second one. What have you learned over the last few months about how you communicate and what you do and continue to discover to a mass audience that are not used to processing raw scientific data?
I think in general the media has had excellent access to scientists. Basically everyone who wants to speak. We do not have sort of we don't diverse this through one person. So the media can reach us as they want. And I guess each of us, yeah, we may have somewhat different philosophy, but we do our best to explain everything we know. We don't hide anything. we try to explain. And I think each of us is learning to try to use simple wording. We have been explaining some very complicated scientific methods and results for everyone here in Iceland. I mean, the national TV, like I have been on national TV explaining how the technical satellite radar interferometry works and how people should read interferograms, and the geochemistry group has been explaining geochemistry, and we need to be very careful. What I find is, normally when I open my mouth and start to speak, there's a flow of terms and definitions that nobody understands. So we have to be very careful. So mass audience not used to processing raw scientific data, we need to do our best to explain as simple as possible. Thanks.
Okay. Thank you, Freystein. So another question for Nicholas from Caron. So if you were to choose which of the older models fits best with the newly obtained model of yours, which one would it be?
So yeah, I had seen the question in the comments. So there are quite a few. So it's a hard choice, but I would say that I would pick among the body wave models to pick something that is different from what I'm doing. And among them, I think I always looked at a model that is surprisingly old, which is the UU-P07. So it was made in 2007 by Amaru and Spackman. And actually, I can prop it up just a second, if that's okay.
Yeah, sure.
I think I still have it open. So it's the one that I was showing when we are benchmarking our results, and it's a P-wave tomographic model. So let me move this around, and so it's this one that is beneath here. Sorry, I just realized it was buried by layers of animations. So it's the one here in the left, and what is interesting is that it's relatively old, but it's made with a very large data set. So in this sense, it's made with a similar approach to what we have been using. And what I like particularly about it is that, differently from many models, it basically, in the upper mantle especially, where it doesn't have data, it actually puts no value. So while a lot of models interpolate, and sometimes this is difficult to makes difficult to assess what's the resolution actually of the model in this specific moment, this model itself actually does not interpolate at all. So it's actually quite clear to see where it actually does see things and where it does not. And I find it also surprising that, being more than, at this point, 14 years old, it's still very consistent with cutting edge models have been only published a few months to a year ago. So I would say definitely this one.
Great, thank you. Moving on to GROW, Thomas asks 2 questions. Can you identify fractures in orthophotos prior to the fissure extension? And are you planning to also add a thermal camera to your overflights, or is this happening already?
This is not happening already, and we have had 2 thermal overflights to my knowledge. I have not exactly seen the results yet to this. At the current setup, I'm not sure with this plane that we can have thermal cameras. In that case, the thermal camera has to be smaller than the camera that has been deployed at this point. But it would definitely be extremely nice to have both thermal data and get the thickness maps at the same time. That could be amazing. With respect to the fractures, so it depends on how the data is being processed. We can have the first ortho images we are getting are around 20 centimeter per pixel. They are kind of too coarse for seeing most of the fractures that happened before the eruption. 5 centimeters you are capturing more, but I think some of the drone surveys that were carried out before and during the extensions of the fissure have been capturing this quite well. So there are high resolution drone images that are available, and people are looking at these fractures that have been evolving both pre-eruption and syneruptive fissures. Thank you.
Great, thank you. Evgenia, Christine Kruger asks, what's the accumulated SO2 release to the atmosphere until now, and how does this compare with Holophone? You're on mute.
I saw this question. I was just trying to do a quick calculation of it. Yeah, it's much smaller than a holophone. It's still, so holophone obviously went on for 6 months, and this has been going on for just under 3 months. So even that alone is already reducing it. So holophone put out about 50 times more than this eruption has done so far. And the total amount is about 250 kilotons.
Great. So we've got one more question for Evgenia, and then we have a few questions for anyone and everyone to answer. So I'll ask the last one to Evgenia, and then we'll move to like open questions. So Ben Ireland asks, do you speculate an impact on health impacts from the eruption due to mask wearing because of COVID-19? i.e., could mask wearing lessen significantly the health hazards of ash, heavy metals, etc., or are these particles too small?
Good question. Very topical. I would think it has had no impact because very few masks actually protect the user. So it's only very high quality, very expensive masks that protect the user rather than the people around them. And most people do not really wear those kinds of masks and do not wear them in a way that really protects themselves. So I would be very surprised if it had any measurable impact just based on that.
Thank you. So we're going to start the everyone questions with the one that everyone wants to know the answer to, but no one can give an answer to, but we're going to ask it anyway. How long do you think the eruption will last?
Yeah, who's going to take this?
Can we do a sweepstake?
Yeah.
I can take it.
Yeah, go ahead, Tristan.
Yeah, so how long will it last? It's an interplay. We have a magma body that is feeding this eruption that seems to be large, and we are not seeing a drop in pressure. It may be fed from below, as the geochemistry was suggesting that there are different melts involved, so there may be magma coming in. I would argue if this process continues as it is, we would expect to see a decline in the flow rate because of reducing pressure that in the source that is feeding. And since we haven't seen this decline in pressure on a timescale of months, so I would say the eruption will go on longer than the rest of this year, because that would be the timescale I would expect for a pressure drop to evolve. However, there can be something that perturbs the system. For an example, an earthquake could change the stress conditions in the magma conduit that is feeding the surface. So if the conditions change because of something like an earthquake, this could happen. Also, what we have learned from the unrest episode, this is a part of an unrest episode at Reykjanes Peninsula that began in December, is that there is links between activity in one system. So if one system is active with intrusions, it is maybe less likely that another is undergoing same kind of unrest. And for example, this began with intrusions in Svartsengi area on the peninsula. When that stopped, activity picked up in another. So I think a very possible way to stop this eruption is if a new eruption starts in another part of the peninsula, because there might be pressure effects between linked either magma bodies in the crust or through the asthenospheric melt layer at depth. So this is my answer.
Great. Does anybody else want to add, or should we move on to the next question? I'll take the silence as we'll move on. John asks, do you think the melting processes that generated the magma are still happening and continue to supply the eruption with new magma, or are we looking at a fixed batch of magma that's simply being erupted? Anyone?
I don't know who should answer this, but I don't think that we actually know this. Probably there is a continuous magma supply, at least based on the answer what Preston just gave. Now we don't have any reason to think that anything has stopped so far.
Great.
I don't know if this is an answer.
Yeah, well, I think we're running out of time, so I'm going to head it back over to Owen, and so you can close out.
For sure. Well, again, yeah, we have about a minute left before this is over. So first, I just wanted to thank all the speakers. Thank you so much for your willingness to finish up some semesters and jump right into more work and take this on with us. It was an incredible webinar. I think I learned a lot, and I hope all our audience did too. Again, thanks to Heather Naley and Victoria Forlini from AGU, Carmen Gaina from NORAM, Morgan for moderating and taking care of the questions, and all of you for joining us today. Really appreciate it. And we will, the last thing, we will get this posted on the AGU website Heather and Victoria said, we'll essentially get this thing processed, clip it up, and get it posted, and all people that have registered for the webinar will get a link to access that. And so, yeah, I hope everybody enjoyed. Thank you so much for being here. Take care.